cannot run experiments of different universes. We cannot actually put a small model universe in a box. We do it in a computer.
We can project out another 1,000-fold in the data volume over about the next 10 years. So we can see that we're going to need to sit on that bleeding edge of supercomputing for at least another decade.
Largely due to the faster interconnect, the Aries versus the Gemini interconnect, we're seeing about somewhere between a 3 to 5-fold speed up for the same computation.
Yes, it's a big data problem, and it will only get bigger as resolutions get smaller.
It's not just so we can get our results faster. It's not just so we can do more data. What we're really hoping for is that having our data there at a supercomputer can lead to a science gateway where more people can have access to this data, where more people can play with the data.
NERSC is the National Energy Research Scientific Computing Center. NERSC has lots of users. We have 4,500 users that run lots of different codes. And so we wanted to buy and procure a system that would do well on all of those applications. And so we felt like Edison, with its architecture, was the best suited for our workload.
Informally, I'm referred to as a beamline scientist. I work at the Advanced Light Source, which is an X-ray facility. It allows us to do X-ray experiments that you couldn't do anywhere else. The instrument that I work at the ALS is an X-ray imaging instrument focused on high-resolution small parts. So we're usually not doing big things. We're imaging small features, sort of like a high-definition CT scan, basically. And we apply that technique to a whole bunch of different areas. We're imaging things for earth science, for material science, for biology, just in all kinds of different areas. Because we're actually collecting 2D images, and what we want to generate is 3D images. So there's a bunch of processing that has to happen. We have to go to a supercomputer to achieve that. And what this improved analysis allows us to do is actually collect less images to get the same results. We can actually collect data sets faster and get better time resolution, as well as just get better images in general.
The Edison system so far has proved very popular with the users at NERSC. I think some of the reasons are the high-speed interconnect that includes both access to the storage system and communication between the processors, as well as the Intel processors that are in the compute nodes that have been performing well on many applications. At least I've heard anecdotally from a number of the users that they're very happy.
Each 36-hour production run produces about 1 second of simulated data. So it's 16 36-hour production runs over 3 weeks if it were continuous computing. And that was on Hopper. The thing about Edison is that Edison we have found to be about 2.5 times faster for our particular code and our particular production runs. So that reduces that time to something on the order of just over a week, which is a lot more manageable, particularly when you have queue times, workflow and getting through the queue, looking at the data, moving the data after a production run and between production runs. The reason why Edison is faster, we think, is that our code is memory bandwidth limited, okay? And Edison has larger memory bandwidth than Hopper, or it could just be it's plain faster. But 2.5 times, it's significant, and I/O has not taken a hit. Performance has been great, up to 100,000 processors.
NERSC has always focused on sustained application performance when we have acquired systems. Since we have such a large community of users, and indeed at any one time we tend to run somewhere between 100 and 300 different jobs on the machine, it's important to us that the sustained performance of the applications be maximized.
We use supercomputers to allow us to do research and simulations that would otherwise be impossible, too expensive, or too dangerous.
I lead a research group focused on direct numerical simulations of turbulent combustion, looking at really fundamental aspects of turbulence chemistry interactions. This image is one of the species, formaldehyde. It's a stable intermediate species that's a marker of some of the autoignition that occurs ahead of the lifted flame stabilization point. We can see in great detail the concentrations of these species and how they interact with both underlying velocity field and temperature and some of the other major and minor species.
Only 5% of the matter in the universe is something that we understand at all. Right? So 25% more are in the form of dark matter, which we have some idea what it is, but we don't know exactly what it is. And then additional some 70% or so are in the form of some mysterious dark energy, which we really don't have any physical framework for it. And it is actually a challenge for a standard model in physics. By going after this cosmological modeling and studying large-scale structure of the universe, we are trying to address what is really the universe made of. That is also one of the stated goals of Office of Science in the Department of Energy. One of the missions is to understand all forms of matter and energy. So this is in a way directly addressing that.
One of the interesting aspects of the XC30 design is its configurability, the fact that you can replace the processors. We are very interested at NERSC in trying to both serve the current user community with their application needs, but also trying to move the community forward to advanced technologies such as energy-efficient processor designs and trying to balance the computing that they need to do today with where we think they're going to need to be in the next 5 to 10 years. So the design that's inside of Edison really gives us a lot of flexibility to be able to upgrade certain components while maintaining the value of the investment that we've made in the overall system.
The driver with this is the big science, is understanding the cosmos. We're addressing those questions that humans have asked ever since they've looked up at the sky at night. How did we get here? Where did we come from? What's the universe doing? What's its future going to be? What was its past? So these are the fundamental questions that we're asking with these kinds of observations. I've been working on analyzing data from observations of the Big Bang. So these are the photons created in the Big Bang, which we now call the cosmic microwave background. The expansion of the universe since the Big Bang has stretched these photons from being unimaginably hot at the beginning of the universe to being 3 Kelvin, 3 above absolute zero today. So very, very cold photons. And background because these are the primordial photons, these are the photons that come from behind everything else. Planck was first conceived in the late 80s, early 90s. It's really been a long-term plan. We knew that we needed to do this extraordinary amount of computing. We were going to have this extraordinary amount of data, but there was no way we could handle it on the computers that were available at that time. And so we were just going to have to progress and rely on Moore's law in computing to carry us to where we needed to be in 10 years' time. So we've gone through 5, 6 generations of supercomputers here at NERSC, most of which have been Crays. And so with each generation, we've been able to get one step closer to what we always knew the goal was going to be. It's sort of just-in-time computing. Edison is arriving just as we need to generate the largest simulation set to support the analysis of the data that will be published next June. We don't just analyze the data. We have to generate simulations of the data in order to understand the statistics of what we're seeing. We have one real data set. We'd like to have 10,000 simulations of that data. So that becomes the completely dominant calculation, where you had to try and read in this huge volume of data and analyze it and then write out some results. Now we do that all on the fly, so that when you start running your analysis code, the first thing it does, completely unbeknownst to the analyst, is generate the simulation. So you say, show me this data, and that data doesn't actually exist at the point where the analyst starts running their code. And under the hood, we've developed all the infrastructure and the interfaces to generate that synthetic data on the fly, avoid all the I/O issues, and really enable the kind of speed-ups that we've needed to be able to exploit systems like Edison and to be able to generate tens of thousands of realizations of the data.
We're really excited to have some of the most energy-efficient computers in the world. We work very hard to make sure that the amount of science we get for the amount of watt of power we put into our systems is as high as possible. Edison is an incredibly efficient computer system, and it's pretty novel in a couple of approaches. First of all, they have the air moving transversely down the entire row, which is extremely efficient for us. It means that we're using the same air to cool each compute cabinet as it's moving through the system. With our previous generation, we had 22 air handlers. With Edison, we can do it with 2. And then that heat is directly captured through a radiator that sits between each of the compute racks. So the energy transfer and heat transfer directly into the water system is extremely efficient for us. We've got the entire cooling loop now down to right about 15 kilowatts of power use compared to a 2.5 megawatt compute system.
I think the exciting thing about NERSC and what we're all passionate about is really enabling science that benefits society. I think a lot of us are really here for public service. There are lots of very high-paying computer industry jobs here in the Bay Area. But really what drives us and what gives us passion is that we want to see there be a broad range of scientific breakthroughs that really benefit all of us.